to Giovanni Di Fratta from TU Wien, and he will speak about skyrmion in spherical technology.
Okay, so thanks a lot for the invitation here. So this is a joint work with the Valerius Lastikov and Dzyaloshinskii-Moriya, although before going to the specific result, I will introduce the model and try to give an overview of micromagnetic theory from the 3D bulk model to the 2D for curvature film, and then we focus on the case of the sphere, and on that geometry we give some result about the existence of magnetic scheme. But let's give it in order. How we go? This doesn't work. So what are skyrmions in general, which is a more general concept with respect to magnetic skyrmion. So let's start from skyrmions. These are defined as class of solitons, which means that in some sense they behave like waves, meaning that they have some shape which brings some energy. And the shape of this wave packet does not change in time. Then we have that these are topologically stable, meaning that although this configuration maybe does not globally minimize what we will see as the magnetic energy functional, still these are the minimizer in some homotopy class. And this makes them topologically stable, meaning that if the global minimizer with respect to this configuration has a lower energy level, still to pass from this configuration, from the magnetic scheme configuration to the lowest energy level requires some discontinuity in the process to some well-known theorem that we will see. So in some sense, topologically stable because they minimize the energy in some homotopy class. And to pass from one homotopy class to another one, you need to put some energy into the system. Okay. So with the quasi-particle properties, this means that they behave actually like particle, but they have a kind of collective in nature, which makes these entities more complex. And the other name to this nuclear physicist, Tony Schirm, who actually studied at Trinity College in Cambridge, who proposed this nonlinear theory, field theory for stable interactive particle. So 1962, but the paper is from 1961. There's something wrong. Okay. But this is the paper where he proposed this model of skyrmions to treat in a different way elementary particles. And since that moment on, this kind of configuration were surfaced in many other branches of physics, like in Bose-Einstein condensate, quantum Hall effect, in nanoparticles crystals, and what are more important for me is as magnetic skyrmions in magnetic thin fields. Okay, so what are magnetic skyrmions? These are kind of swirling topological defects in the magnetization texture, and which have some characteristic topological charge that in the context of magnetic skyrmion is called the skyrmion number, and can be characterized in integral way by this integral due to Kronecker. And actually there is a result of Adamart which says that this is kind of a representation of the topological degree of a configuration. And you can define this, we're interested in the case of R3 for every compact hyperspace of R3, or even for the full 2D domain, as soon as you have a uniform configuration at infinity. So in some sense you can think of this as a sphere as well. Okay. So yes, right. Okay, this is what I was telling before about topological protection, because this magnetic skyrmions have some characteristic topological charge. And due to Hopf's theorem, skyrmions which has different topological charge cannot be continuously deformed one into the other. And we will see many pictures later on, but this is just the typical two magnetic skyrmions that appears in let's say in thin films, okay, the block type skyrmion and the nil type skyrmion. They just differ in the plane in which this configuration rotates. So you can imagine that you have this disk, and then you plot the radial direction of this on this disk. You have the plane on disk, and then you have a perpendicular plane to the disk, and according if the rotation in this section on this plane is along the plane or is in the plane or perpendicular to this one, you get this kind of configuration. You can see you can see the kind of a section here of the sense of rotation. So, where this Magnetism-Moriya comes from, because up until 10 years ago, they were thinking that all the phenomena, possible textural magnetization that you can see in magnetic material are how to say, the result of three main types of interaction, which is the symmetric Heisenberg exchange interaction, which you on say on discrete level you can describe in this way, where Si and Sj are the spin, and Jij is kind of a constant which weights the interaction among the spin in position I in the lattice and in position J in the lattice, and then magnetocrystalline anisotropy, and usual magnetic bipolar interaction. They were thinking that these three kinds of main interaction were able to explain no textures that are visible in micromagnetism, at least in magnetism on the nanoscales. But then it happens that in a work by Bode, this group reported the observation of textures which were, how to say, unusual. And the formation of this texture, because if you see experimentally this texture, they are stable, could not be explained by just considering these three main contributions. So they link this to some previous observation of Dzyaloshinskii-Moriya that they propose. They propose that actually what happens is that the Dzyaloshinskii notice that if you have a periodic material, so if you think that like a multi-layer, which there is every layer is made by different magnetic material, but in a periodic way. So some of these materials repeats. And if you take some special particular ferromagnetic material, you consider these layers, he was observing that the main configuration, so the global minimizer, is something like an helicoid. And so he proposed that the fact that you can see this kind of helicoids is due to the fact that there is another kind of interaction which is anti-symmetric, which nowadays is called called the Dzyaloshinskii-Moriya interaction, and which has this shape. So you have the classical Heisenberg exchange interaction, in which interaction is symmetric, meaning that you can swap Si and J and the energy will not change. And then you have to add this contribution, which is anti-symmetric. And more specifically, what does it mean? It means that this kind of energy will distinguish between these two configurations. If you have a spin which goes on the left and then on the right, is different if you take first a spin that goes on the right and then on the left. So you want to distinguish between these two configurations. You can do this by considering this kind of contribution which are not symmetric. And depending on, this is called Dzyaloshinskii vector, this vector here. And depending on the symmetry property of the crystal lattice of the magnets, and according to some rules which are established in Moriya papers, you can derive the expression of this vector dnj, and then consider the full model in which these contributions sum up. Okay, so let's see why we are interested in this scheme configuration. Mainly interested because, according to Albert Fert, this okay, let's put it this way. Stuart Parking some years ago proposed in order to overcome to go to high density storage technology, proposed to embed 2D structure in 3D. So they proposed this model in which the magnetization moves in a nanoribbon, and was proposing this strategy to overcome the limit of density in magnetic storage technology. And what happens is that there are many difficulties to overcome if one wants really to push this direction in applications. And according to Fert, these quasi-particles have all the properties necessary to overcome these difficulties that were proposed in the scheme of Stuart Parking. So we're interested because it seems that you can really move on a ribbon these quasi-particles, read them, write them, and so to be used as logical bits. Okay. So let's see this. Okay, I did cite exactly the words of Albert Felt. He says that although the exploration of the world of magnetic scheme is just the beginning, because this is true, so it's quite very new topic in the magnetic community. This particle can, apart from interesting fundamental interaction, they open the way to devices for ultra-dense information storage. Okay, so we are interested in magnetic skyrmion. Let's see how can we can do mathematical analysis on this. We have to start from the micromagnetic model. Many of you are familiar with this. So this is a continuum theory of a magnetic particle on the nanoscale. So it's in the on the mesoscopic scale. So the intermediate scale between classical Maxwell equation and quantum mechanics. And it dates back to this seminal work on Lipschitz on fine ferromagnetic particle. And this is a variational theory, strongly nonlinear, which affects, we take into account effect from different spatial scales. So from the short-range interaction, like exchange that we saw before, to magnetic ones, which are long-range interaction. And what happens that according to this theory, okay, when the magnet is a temperature which is below a critical value called the Curie temperature, the modulus of the magnetization is uniformly spaced. So you have this, that your configuration. So let's put in this way. This is a kind of classical theory. So you have a classical vector field M, the magnetization, which describes the status of a ferromagnet at the nanoscale. And this vector field must satisfy the fundamental constraint of micromagnetics, which says that when the magnet is a temperature below the Curie temperature, the magnet is always locally saturated. It means that the modulus of the magnetization, this vector field, will be constant, just the modulus. Of course, the direction will change. So the modulus of M is spatially uniform. And the important thing is that the alignment of this magnetization can be changed by applied external magnetic fields. This is important in when you want to say write information on magnetic supports. Okay, all that is summarized in this energy function. So the observable state of magnetization corresponds to the local minimizer of this energy function. And this is a non-local problem to the presence of the stray field, this term, HD, which is the classical Maxwellian interaction. Okay, these are the Maxwell-Ampere equation of magnetostatics. And this energy is called the magnetostatic self-energy. This gives you the non-local contribution to the energy. Then it's a non-convex problem just because the magnetization is constrained to take value on the unit sphere. Of course, this, as soon as you fix the temperature of the ferromagnets, you can assume that your magnetization after rescaling is just takes value on the unit sphere. So the non-convexity comes from this constraint. And then let me really briefly describe what are these terms. This is a classical term that you have also in the last history. So this is exchange energy and penalized non-uniformity in the magnetization texture. Then the second term in red here is the crystalline anisotropy energy. And model, yes, it models the existence of preferred direction of magnetization in the crystal. And this direction are called easy direction, and you can model this by introducing a function defined on S2, which is usually assumed to be 0 just on the easy direction. So it's a positive function which is 0 just on this easy direction, and so this contribution favors the alignment of organization along this direction. Okay, do not dwell on this. Magnetostatic self-energy is the contribution that is here, and as I told you, this is the non-local interaction term, because for every magnetization you have to solve this problem, then plug the result here with the energy, and then you have to see if this is minimum value, you have to go down with the energy. And the last term is the Zeeman energy, and I told you that takes into account this effect that if you apply an external field on ferromagnets, the magnetization tends to be aligned in the direction of the external applied field. But we will see that for our purpose, we can completely forget about these terms of the Zeeman energy and this anisotropic energy, because at least when we study to delimit this behaves like continuous perturbation, and so not only they are, it's simple to study them on each one, every one of these terms. But still, the result of the analysis for this result can be summed up to the other terms. This is not generally true for gamma convergence result, but I will say more later on. So, but we were interested in magnetic scheme. I spoiled a little bit the presentation. So now I tell you how can we treat this effect, the Dzyaloshinskii-Moriya interaction in micromagnetics. So in order to do calculation on that. But the main aim of this talk is to show that if you focus on not on thin film, so on planar thin film, but on curved thin film, then you can still observe these magnetic skyrmions without the necessity to introduce this Dzyaloshinskii-Moriya interaction. So in the last period, people start to be interested in this curved geometry because they observe that curvature can replace the role of the Dzyaloshinskii-Moriya interaction. So, just to say once and for all, while in plain film, to explain what you observe, you really need to add something to your energy function. This is not the case for curved thin film. In curved thin film, you can still observe a magnetic scheme, so configuration, minimized configuration with the non-trivial topological degree. And this can be observed and explained also theoretically without taking into account the Dzyaloshinskii-Moriya interaction. But of course, to point out this, I have to tell you what is how we can model the Dzyaloshinskii-Moriya interaction. So mainly there are two kinds of Dzyaloshinskii-Moriya interaction, and they all can be treated as some invariant of the Lifshitz-chirality tensor. This is the bulk DMI, which you can see in any magnets, and interfacial DMI, which appears when you have, say, multi-layers, and this kind of antisymmetric interaction that appears at interface between a magnetic layer and non-magnetic material, roughly speaking. So how we can model the bulk DMI? The bulk DMI is just how to say. In principle, you can if you take the summation that I showed you at the beginning, so the discrete one, you can just do some formal computation if you wish, and you will really come out with this expression that you see here. So this term carlm.m. So who is familiar with the Ozen-Frank, this is kind of term that is also present in the theory. And this kappa is just a constant called the bulk DMI constant, and this sign determines the chirality of the system. So I don't know, if you have an helix which goes right-handed, is right-handed, by changing the sign of kappa, this helix is the minimizer, which is, if the helix is the minimizer, the helix will be left-handed now. And then you have this interfacial DMI. Okay, this is a little bit more involved also to do a meaning, a formal meaning to this guy if you are in standard function spaces. Okay, I will not dwell on this. Just important that there are two main classes of the Dzyaloshinskii-Moriya interaction that accounts for all the studies that are currently investigated. Okay. So let's go to what is really propedeutical for the result. So magnetic thin film. This has a long history. This topic. So mainly what happens is that you take a surface, you extrude along the normal direction this surface, and you get what is called a shell. You know that if the surface is compact, but also under less general hypothesis, you can always find a tubular neighborhood. So it really makes a sense to talk about the shell. And so this tubular neighborhood will be described in this way, and epsilon will be the thickness of the shell. And then you can ask yourself, if I start to compute the minimizer of the micromagnetic energy function on this shell, and I shrink the thickness of the shell, I would try to understand which is the behavior of the minimizer when epsilon goes to 0. So we are real in the realm of gamma convergence here. Okay, everyone of you will expect that it's easy to prove by direct methods that this function always has a minimizer. And then, so the problem is like this. You have your energy function, you divide by epsilon to get to avoid an informative result, because otherwise the limit will be 0. And you ask which is the this family of minimizer to what will converge. And yeah, feel free to stop me any moment because I work since a long time on this topic, so I'm not more able to distinguish what is well known, what is trivial, and what is strange. Let's put it this way. So the first result on this direction is the result of Joy and James, in which they take into account the case of a planar shell. So you take a 2D domain, you extrude along the EZ direction, and you want to understand which is the 2D limit as you shrink this this planar shell. And they found that actually what happens is that your magnetostatic self-energy, which was not local, now at the leading order becomes a local term. So that the magnetization tend to favor in-plane configuration. Actually, if you don't have an isotropy, it's clear that the whole configuration will be uniform and in-plane, because this possible quantity, this will be 0, and m dot 3 will be 0. And they generalize what was already known for ellipsoid, so through the works of Stoner and Wolfram. Then what happens is this work of Carbo, in which, okay, I have to go back just a second. As I told you, if these two terms are, if there is no anisotropy, here clearly the minimizer are constant on this surface, and are in plane. And the minimum energy will be 0. But if you want to gain more information about this, you have to go to the second order. This is something that did Carbo, maybe also you, okay? Sorry if I forgot, but you will be silent for something else. So, and what happens is that if you go to the next order in gamma expansion, so if you want to have more information about the minimizer, you discover that the expansion goes like this. So at the 0 order, although there is this epsilon, you get the model that we saw before, and then at the next order, you see that you have to minimize this quantity, where psi now is an in-plane vector, along where nu now is the normal to the boundary of this domain. Okay. So you have among all possible in-plane configurations, the utility will select the minimizer which minimize this energy function.
There's only one problem, which is the scaling. It's epsilon square ln of epsilon.
Say again, where here?
Yes, it's epsilon square ln of epsilon.
I didn't listen. Epsilon square?
Multiplied by ln of epsilon. Logarithm.
Okay, yes, you're right. Yeah. So let's go, but this is the work of Carbo, yeah, so. So what happens, yes, then I told you there are different regimes that people were investigating, and okay, and Carbo also treated the case in which you have a curved thin shell, so you take a curved surface, not a planar surface, let's put it this way, you extrude, and then you want to understand what happens to the at the leading order. And he did this just for surface which this technical assumption, which is that this surface must be diffeomorphic to the closed unit disk, so in some sense must be a kind of graph of a function. And then there is this work by Valeri, in which he treated this what I call like pillow-like shell, because you have two functions which the extrusion is not uniform, but is driven by these two functions f1 and f2. So what you will get, it will be a shell like this, so the thickness will not be uniform. And what is interesting here is that at the leading order, the magnetizing field, and so the magnetostatic self-energy will not more be local, so you will still have a local function. Okay, so as I told you, why people are interested in micromagnetic energy on curved and thin film is because you discover that for this geometry you don't need to have a minimizer with non-trivial topological degree. You don't need to take into account the Dzyaloshinskii-Moriya interaction. So it's just the curvature that lets you how to say permit the formation of magnetic skyrmions the spontaneous formation of magnetic ischemia, meaning that this configuration will be stable, although maybe they are not the global minimizer of your energy function. Okay, let's see if I'm forgetting something. Maybe I also check how much time I have, just to see if I'm running. Okay. So, what happens is that there is a huge community in Kiev which is working on this curved thin film. And in working in this field, they assume that the work of Carbo still holds for when you have for general surface, for general compact surface, not just for surface which are diffeomorphic to the closed unit disk. Actually, this is true, and then but the proof we usually require some technical assumption, but that now with Valery we were able to overcome. So, long story short, it means that when you work with the compact surface and you do this process of studying the leading order behavior of a family of functions defined on this shell, what you will get is this function. So you will get the tangential gradient of your configuration plus this term, which is u0.nu, so where nu now is the normal to the surface, and plus these two terms that are really important for physical application, but actually are not so interesting for the mathematical analysis of the problem. So all that said, I can really focus on although these are where all other results, so I can really focus on the title of the talk. So because now you will believe me that more or less that the functional, if you have a sphere, then you want to study the limiting behavior of the minimizer on a thin shell. What you have to study is this energy function. So when I say H1, S2, S2, I mean that these are the sublet space defined or function which are defined on the two sphere and with value in the two sphere. And you have to study this energy function. Well, this kappa here take into account both the stray field, the magnostatic self-energy, and also the presence of the crystal anisotropy. Meaning that just the magnostatic self-energy will give you some constant here which is positive. But if you allow this constant also to be negative, this take into account also the crystal structure of your thin field. So some consideration really is consideration. Of course, uniform states are the only locals, also global minimizer when kappa is equal to 0. When kappa is greater than 0, you tangential vector field are energetically favored. And when kappa is less than 0, energy minimization prefer normal vector field. This is the first thing that one is immediately see from the expression of this function. But still, the analysis, because we tried with many techniques to try to characterize the the global minimizer of this energy function, and we were always trying to do this without
one question. So K negative, meaning that you need also some anisotropy to get K negative.
Yeah, exactly.
Because just the magnetostatic is positive. Yes.
Yeah, exactly.
Okay. Okay. Thanks.
So, what we can say for kappa greater than 0 is almost nothing. We can just do some trust some experimental, some numerical simulation, which shows you that for kappa greater than 0, there are two quasi-tangential topological projected states, which are called the vortex and the onion. This is the vortex states and this is the onion states, and they both have topological degree 0, these two configurations. And the kappa for the onion, kappa positive for the onion state is less than kappa vortex. This is what appears in simulation. And then you have also this state which has topological degree 1, but it's not clear according to some experiments. Seems that this according to this, it seems that this is while these two seems to be global minimizer, this one not. So, okay, the guess here would be at least if you do some proper change of coordinates, you see that there is some symmetry. You can really see, for example, this is one of the pictures that I showed you at the beginning about block walls. block type skyrmions. Anyhow, this part is still open, say the case kappa greater than 0. But for kappa less than 0, we were able to say many things. And the idea was really simple, was to relax the constraint. So instead of penalize, we really relaxed instead of using classical penalization techniques, we really relaxed the constraint by, instead of assuming that the modulus of m takes part on the unit sphere, we just assumed that the L2 norm of m is equal to 1. And then we were looking for sharp estimates, so for sharp inequality of this kind in such a way that we, how to say, we could find sharp lower bounds to the energy level. And this asked for to prove sharp Poincaré-type inequalities. So we were looking for inequalities like this type with gamma possibly the best, the optimal constant, and we succeeded in this by the means of by using vector spherical harmonics. I will go to that soon. But just want to tell you that this is a kind of interesting problem, because all the apart that this inequality, Poincaré-type inequalities on the sphere, has application in many other branches, say, of mathematics. But to say, after a deep bibliographic research, it appears that when okay, it's a little bit small, but the sovereign inequalities on two sphere fails when n is equal to, more or less. Let's put it this way. At least some inequality or blows up or is meaningful when okay, is unuseful when n is equal to 1. In fact, when you are on S2, some of these inequalities are replaced by some other inequalities to work in other contexts. So the idea was to use vector spherical harmonics, but you can, while scalar spherical harmonics are quite standard, you have many different vector spherical harmonics, and you have to use the right one for the depending on your purposes. So we were, it's actually these vector spherical harmonics are quite used in geomathematics. So we use vector spherical harmonics, and we found that our problem reduced to, we were able to reduce the problem to still an infinite dimensional one, but on the space of sequences, as is classical in this setting. But then we, by writing the Lagrange equation on this space of sequences and playing with the equation, we realized that that the problem is can be reduced to a finite dimensional one. So as a problem from S2 to S6 to R plus, and then you can obtain a complete characterization of the minimizer. So I will give you the result. For any kappa in R, for every u in H1, S2, R3, you have the following inequality. And the best constant that you can choose here, gamma kappa, is given by this possible value. So for k less than or equal to -4 is kappa plus 2, and then this other guy for kappa greater than -4. This is just a remark that if kappa is less than 0, you can rearrange the equation in a way in which everything is positive on the left-hand side and the right-hand side. And the interesting thing is that this inequality is really sharp. So this is a kind of plot of this gamma function for kappa greater than 0, and then for kappa less than 0, we plot kappa plus modulus of kappa plus gamma kappa. And this inequality is really sharp, meaning that we can characterize the minimizer, and these are a combination of vector spherical harmonics. Okay, he will. I have been many times on the other side of the room, so I know that that would be completely useless to go to this. We can discuss later if someone is interested. But I mean, the important point is that you can really characterize in a simple way also the minimizer. And also we recover by, okay, although I didn't put this in this slide, you can recover the classical Poincaré inequality on the sphere for tangential vector fields. Okay. So let's go here. So that was the question when the inequality is exactly reached by this combination of vector fields in which the coefficient must be chosen according if kappa is less than -4 or is greater or equal than -4. And just to remember this vector spherical harmonics, these y and j are the classical scalar spherical harmonics, and you introduce this complete system of vector spherical harmonics by taking the classical spherical harmonics multiplied by the say backside. This is the normal to the sphere. Then by taking the surface gradient of y and j, and taking what is called the surface curve of y. And you can see that these two vector fields are really tangential. These are two tangential vector fields, but this is along the normal. And if you see here, you see that this component does not play, this vector spherical harmonic does not play any role in the minimizer. So you will have this one which is along the normal, this one which is along the normal as well. And then the tangential part of the vector field just comes here. And I would like to finish by showing you some pictures. So to almost finish by showing some pictures. So for these are the value of the minimizer of the relaxed problem. So here we are not imposing that the vector field has value on S2, just that the L2 norm is equal to 1. And so you have for kappa, say, sufficiently negative, you have a kind of normal vector field. Then as soon as you go towards k equals 0, you tend to reach, of course, a uniform configuration. Well, but what is interesting is that at least for these vector fields, which are a minimizer of the relaxed problem, have unit modulus. So we were able to prove that plus and minus n, so the normal vector fields, are actually not only stationary points of the magnetic energy function, this for every kappa in R. You can see just by writing the Lagrange equation. But they are strict local minimizer for every kappa less than 0. Oh, that is the yes, a strict local minimizer for every kappa less than 0, and they are unstable for kappa greater than 0. Also, for kappa sufficiently negative, the normal vector fields are the only global minimizer of our function. So now we are talking really, we are coming back to the micromagnetic settings. So we're able to prove that on the sphere, there are magnetic schema configuration. These really are the plus and minus the normal vector fields. And actually, these two configurations really have two different topological degree, because plus minus n will have the topological degree which is plus and minus 1. So if you, in principle, you can think that you can memorize information via these two states, because as soon as you are able to impose a plus n configuration on a sphere, then there is no way in which you can pass to the other one without forcing really putting a lot of energy into the system. So this I just have to.
Question.
Yeah.
What's the sense of local minimizer? What do you mean? What kind of local minimizer? Local minimizer in H1 or?
Yes, in H1. Yeah, sure.
Okay.
Yes, this is in H1. Because what we do is that you can compute the second order variation, and then via the Poincaré inequality, sharp Poincaré inequality, you can see that for kappa less than 0, the second order variation is greater or equal than some constant for the for the L2 norm of the vector fields. But still, this is a local minimizer in H1.
Okay.
And then you can see that these are stable for kappa greater than 0. So you do an analysis on the second order variation, having now really a sharp inequality to play with. Okay, and what I would like to point that these are the global minimizer, but there is a quite recent paper of Melker in which they show that there exists some non-global some other configuration which have different topological degree. Still for kappa, what is it? Still for kappa less than 0. So for kappa less than 0, global minimizer are plus and minus n, and they're also strict local minimizer. But there is some other local minimizer, and they're showing this paper of Melker, if I say well, right? So let's see. I think that I'm done. So thank you very much. And if you have any questions, we can discuss. Questions?
No, we did not explain much what happens for kappa less than 0 or greater than 0. Sorry.
Yeah, we didn't. We just have a numerical simulation. Let's put it this way. We don't know, and then some paper of some of the.
No, but you at least know the explicit minimizers for the relaxed problem, and they
Yeah,
look
this is
pretty
true.
similar to what people observe empirically for the real one.
This is true. The fact is that you could never hope that also if kappa is really huge, you will have the tangential configuration to play the same role of the normal one due to Hairy-Bolt theorem. So if M is if you have configuration from S2 to S2 and it's tangential, then you are no more in H1. That's the point. So while for normal configuration you can expect in some sense that for kappa really negative, you have this normal vector field as a global minimizer. You cannot expect tangential vector field to play the same role for kappa really positive. So yes, but we are currently investigating the case kappa greater than 0. And no, I mean, what I showed here are not the relaxed problem. These are really the configuration that you had when you focus on H1, S2, S2. So these are this is the aspect of the minimizer. But of course, first of all, we don't know if these are all the minimizer. And then one can of course use some ansatz to how to say to have an expression of this minimizer. But okay, for me, it's still open. It's not clear how to afford this problem.
So maybe a remark. So in the case K positive going to infinity, right? So S2, okay. So so there you can prove, but you should go also to the second order. So where you will see that the curvature comes in. So you can show that the vortices will be diametrically opposed, okay? So, but that's just in the limit. So I don't know, right? Because I mean, you expect that for K positive, maybe at least if it's large enough, then the configuration is symmetric. Yeah? So you really have a symmetry, and the vortices are there. So what we can compute is just that in the limit. So when you at the second order, you will see the interaction between those two vortices. The best configuration when you minimize that renormalized energy is really a diameter. So this is okay. We announced in a paper with Bob Chiral. So okay, the big paper will come out soon.
Okay, you are saying that if I take, for example, this configuration of the vortex, but not with the same.
So you take exactly your functional. The functional where you stay in S2, okay. So in the limit when K goes to infinity, yeah, in your case K goes to infinity, right? You have to be tangent of modulus 1, right? So of course, as you said, the Hairy-Bolt tells you that there is no smooth tangential, but you have these two vortices that appears, right? And those two vortices should be on a diameter, right? I mean.
Yeah. Okay. But I was reading at least in some piece of paper that if you have the how to say, if you pop out from the vortices with the same alignment, then it's energetically favorable with respect to if you go in this way. Is something that you find?
No. So the degrees are always 1 and 1.
Okay. Well, this is of degree 0. What you see here.
Well, it depends.
Well, you can see this from the projection because it goes like this, then it goes back, and it never turn. At least for the definition of topological degree, which is with the Kronecker.
You have to explain what are these two-dimensional pictures.
Well, whatever they are, this is how to say, they are obtained in such a way that the topological degree will not change. Let's put it this way. But these are given by. Actually, okay.
Is it stereographic projection?
Not only this. There are many two different changeable coordinates for the domain, the codomain, and you get this. For this to the initial S2, so you have map from S2 S2. You have parameterization here, parameterization here. These two parameterization must be taken different to have this kind of graph, and also you have. I really rescaled. This is infinity. I mean, I rescaled the image so that this is really what happens at infinity. So one of the points. But Okay, I can tell you what was written at least in this paper from the community in Kiev. They say that you can have you have this topological degree 0 in which the core of the two vortex is aligned in the same direction. And then you get topological degree 1 in which the two core of the vortex are anti-parallel. But they say that these are energetically favorable, this one. So in their paper, at least they say that they do not study, maybe they are wrong, I don't know.
So there is this Gauss-Bonnet formula that tells you that the sum of the degrees should be the characteristic of your manifold. Yeah? So the characteristic of a sphere is equal with 2. That's why the sum of the degrees should be 2 for a sphere.
The sum of
the degrees of your vortices should be 2 because it's the characteristic of a sphere.
Well, but there are many different definitions because you can find what is called the total curvature, the index, and these quantities are not the same. All these quantities that you are saying are not the same. But if you plug this configuration into the Kronecker formula, you will get 0. You're not convinced of this.
I mean, the characteristic is 2 minus the genus.
Well, I think you're talking about the sum of the local degree at each of the vortex is 2.
Yeah.
He's talking about the degree as a map from a sphere to a sphere. It's different.
Yeah. So when I say okay, so when I say it's the winding number, yeah, it's the winding number.
Okay.
Yeah.
So
yeah.
No, I was talking about the full topological degree. So if you take the full topological degree for this configuration is 0, and then there is another configuration which is of topological degree 1, which I think is exactly the shape which is there on the left, in which the two core are anti-parallel. And this has topological degree 1, but they say that, okay, I didn't go really into details, that these one are energetically favorable with respect to the degree 1 configuration. But still, everything is still open for me at CAP, but I will take a look to your paper because maybe I found some answer.
Is it favourable for applications not to have the DMI terms? I mean, are there many more materials without a DMI term for which you would contemplate making a spherical sample to do practical things rather than a planar sample with a DMI term?
Okay, I think that to have magnetic skyrmion, this depends more on the geometry. This is my view. So if you want to have this skyrmion for application on planar thin film, you are obliged to use material which have this property. So like which have Dzyaloshinskii-Moriya interaction, which the Dzyaloshinskii-Moriya interaction is strong. But if you want to use such kind of configuration curved geometries, then you don't need to use material which have DMI. I don't know if I answered your question.
The question was what's the relation between materials, number of materials which have DMI.
I have no idea how many materials there are with DMI and without.
It used to be very difficult to find practical materials with the DMI, and there was a very narrow temperature range.
Exactly.
And so on. I mean, I'm not an
cannot
expert,
answer
but
that.
that's what I heard. But here you don't need it, so there's
No, you don't need it. Yes.
many more materials probably would work. But I mean,
I don't know how many materials
I
have
don't
the
want to guess. I'm asking
Dzyaloshinskii-Moriya.
a question.
Yeah, I understand. The problem is that I don't know how many materials the Dzyaloshinskii-Moriya effect, which is so strong, and which are the material. So I don't know the number of ones with respect to the other. So I cannot really answer.
You don't know, but maybe,
No.
I see. That's my
But I think like you that there will be, in principle, I think that there will be more materials without the DMI than with the DMI. But this is.
I could ask you a more technical question. I mean, so can one include a DMI term on a curved surface? Is there a standard way to write that? And
Yes, there is a possibility. Yes. There is the possibility to write the DMI term also for the surface. That's what you mean.
Yeah.
Okay. Yes. So just to replace the Carlem term with the. Okay, some part of the contribution of this DMI term will go into the anisotropy energy, and some part of this will give you a tangential curve. That is what happens. So the novelty is that if you have this Carlem.m part, say the normal component of the curve will give you a contribution to that k that is written there. So to that kappa, yeah. So it will not be kappa, it will be kappa plus something.
Oh, I see. It modifies that
Yeah.
term. Yes.
And then the other part of the curl will give you just the tangential curl, the tangential curl.
curl.
Yeah. Tangential curl dot still m, or the magnetization of u. But I did not investigate. I mean, I know that the result is this, but I did not investigate say which are the minimizer in this case when you also have the curl m dot m.
It'd be quite nice if there was a continuous theory that went from the curved model and allowed for a variable radius and had a limit, which was the planar model. But the planar model has a DMI term, and your model does not. So I think you can't take this limit. I mean, you can't see this interpolation.
No, but you can unwind the surface and you see exactly the DMI term when you're dealing.
This is something in some research that we still are investigating. I mean, that
Yes.
if you for example write the energy, look at this transformation from the sphere to this disk. If you write the energy as 2D energy, so now defined on this disk, you really have what appears. Although if you don't have any DMI, what appears is this kind of curl m dot m, which is seems to be created by the change of coordinates. Actually, also this guy in Kiev recently, I think 1 week ago, they put this paper in which they say we noticed that by doing this change of coordinates, your to the energy will your to the energy on the planar domain will appear with this curl m dot m term. So it's not clear if this is a real stuff or maybe just some. Okay, I'm not a physicist, so I cannot tell you this, but maybe it's just some imperfection in the 2D domain which creates curvatures, and this gives you these terms. So this could be one of the.
In that case,
I'm sorry, but maybe we should go.
We can discuss.
Yeah.